In this video, we're going to work with complex ions. It's not really a KSP problem, but we will circle back to link complex ions with KSP problems. So I ended up calling this a type 5. It's quite distinct and different from other ones. So there are certain complexes like, let's say we had cobalt, NH3, cobalt, NH3, 6 plus 2. Or cobalt H2O6 plus 2, or Ag NH3 2, which should be plus 1, or Fe SCN plus 2. So you don't get a balance of positive and negative. You actually end up with a charged substance at the end. Usually it's a metal which has a positive charge, and then adding a ligand, which is something maybe with a negative charge or something with a neutral charge, but extra electron pairs like an NH3 group or an H2O group, which would have extra electron pairs on the opposites, and then they combine together. So we're going to look at a problem right here and do a little calculation here first. First off, I'm just going to look at this formation. If Ag plus combines with NH3, it forms AgNH3. NH3 is neutral, Ag is plus 1, so the overall thing would be plus 1. Notice its formation constant is significantly positive, so this thing moves toward products quite significantly. Let's say we try to add another NH3, and it's very accepting toward that too. So it's still going to be plus 1 at the end, but now we got two NH3s attached. Now, what if we want to just do this whole combo instead of step by step, do the whole thing, and we can do Hess's law. Notice we can cancel the intermediate, AgNH3 plus 1, and we get Ag plus 2 NH3 forms AgNH3 2 plus 2. I know it's a little bit hard to see there. So what's going to happen is because we're adding these two things, we're going to multiply the two K constants, and this 10 to the third and 10 to the third here becomes actually 10 to the 7th, 1.7 times 10 to the 7th. And that quite favorably forms the products, or it moves toward the products in equilibrium. So that's what we're going to do is really, I think it's easiest to look at this holistically. Okay, now we're supposed to calculate the concentrations of Ag plus, AgNH3 plus 1, and AgNH3 2 plus 1 in a solution. So let's take a look. 100 milliliters of 1 molar AgNO3 and 100 milliliters of 2 molar NH3. So notice there's a dilution factor. You got 100 milliliters, 100 milliliters, so you got to cut concentrations in half. So for Ag plus, essentially I cut the concentration in half because it's 100 out of 200. I get 5 times 10 to the negative 4th, and I write that in here. And NH3, I'm going to cut that concentration in half. So instead of being 2 molar, it ends up being 1 molar right here. And before the reaction occurs, I don't have anything. Well, it's going to go toward equilibrium, and then we're going to take a look at amounts there. So notice when I try to do this reaction, I want to have a big excess of NH3. So I want this to be a lot bigger than the Ag to actually get it to dissolve better or get it to form this complex better. So what I'm going to do is look at this like an excess limiting reactant. Virtually all of this is going to react because this is so big, and the reaction goes pretty much toward the products. But it will kick back a little bit. Okay, so when it kicks back, it's going to kick back into what? One part of this, two parts of this. So I'm going to call this X, I'm going to call this X. And technically this would be 0.0. This one would lose a little bit of X, but we're going to find X is going to be even small compared to this number right here. So this really ends up being our concentration of AgNH3 2. So we solve for this right here. Okay, the next one, the book will go through a ways of looking at the K2 and the K1 to find this. I think it's a long way to do that. So I'm going to go right to the shortcut method for doing this, which is a little bit different than section 16.3 in your book. And I'm going to just go up here and highlight that if I can find that. Okay, having a little trouble doing that. And we'll scroll back. Here we go. We're good right here. All right, so the shortcut is I'm going to take, instead of look at each one individually, I'm going to look at this overall equation and say K1 times K2 was 1.7 times 10 to the 7th, like we said. And that's going to be AgNH3 2 over Ag plus an NH3. So I have all these things right there. And we determined that NH3, AgNH3 was 5 times 10 to the negative fourth. It really is minus X. We're going to assume X is really small compared to this amount. We're trying to find Ag, and we know NH3 is 1.0 times, or 1.0. So I plug that into the equation, and ultimately, if I know this, this, and this, I'm trying to solve for Ag, I get 2.9 times 10 to the negative 11th for my Ag plus concentration. So that's really, really, really small in this case, if you're trying to solve that. The only thing I didn't solve for is this AgNH3 I could take one of these in-between steps that we showed before here. I wouldn't ever ask you to do that. I highly doubt the AP folks are going to ask you to do that, but you could plug it in and follow along and figure out it ends up being 6.1 times 10 to the negative eighth. So notice this one is the biggest of the three. The Ag with one NH3 is next biggest, and then the least is going to be the Ag plus, which is really, really small at the end. Okay, I'm going to just do one more example of that, and let's take a look here. And these are really the same problems that were in section 16.3 of your book, but I'm trying to just do them a little bit shorter, a little bit more concise. So another ligand looks like it's going to be Ag, and again, it looks like Ag is a +1 S2O3. This should be, let me clear this drawing out a little bit. I threw some marks in here. Should undo that. There we go. Okay, so notice S2O3 has a -2 charge. You might recommend this. This is a magic B crystals from the thiosulfate from the reaction rate lab. This is stuff that turned things clear. But anyway, Ag +1, if I go with -2, it becomes -1. If I attach 2, it becomes -3. So these charges can vary, not too concerned about that. But ultimately, the optimal thing is when two things are attached. So gaining one thing is definitely a 10 to the eighth. Okay, gaining another thing, 10 to the fourth. Those are two things that highly favor the products. Let's combine the two equations together. You can see the intermediate Ag2SO23, and what happens is you get Ag plus 2SO3 minus 2, or S2O3 minus 2, and then you get AgS2O32, and then that's supposed to be a -3 right there, and it's the K1 times K2, which is 2.9 times 10 to the 13th. So that goes extremely much in the toward the products. So again, what I got to do is take my concentration of each one, but I got to go through the dilution factor. Notice it's a 150 and 200, so it's a 150 over 350 here. Gives me some not so even numbers of 4.29 times 10 to the negative fourth. That which goes for my Ag plus concentration. And then for my S2O3, which is going to be a lot higher because I flooded out with that, I get the 5 molar times the 200 over 350, it looks like 2.86. So virtually, because this is such an excess, almost all of this will react. So we assume if this all reacts, it's going to be a 2-to-1 ratio. So I have to double it here, and then I subtract, it still becomes 2.86. Okay, notice what I get here. I get the 0.000429. That is my concentration of AgS2O32 minus 3. What about the concentration of Ag? You're going to do that same shortcut that we used before, and that's probably the other one that you could be asked here. I take that K value, which is 2 times 10 to the negative 13th, and I look at the overall equilibrium constant, which is this over these two things, or Ag S2O32 over Ag and S2O3 squared here. And what happens is I plug in the 4.29 times 10 to the negative fourth from here. I don't know Ag, and I know that the S2O3 is the excess thing right here. Or I'm sorry, yeah, so that's the 2.86. And I look at this, and I get Ag plus, in this case, is 1.8 times 10 to the negative 18. Okay, again, not real. Probably you'll get a question like this, especially maybe digging back this far, but at least knowing the existence of how these things work, and then in connection with a KSP problem, which I'll show in my next video. So again, this is some work from pages or chapter 16, section 16.3. And I think understanding how that equilibrium works here, knowing how to do the shortcut method would be best. I'm not too concerned about all this other detail that they'll show in the book to getting there. But we'll see how that applies to a KSP problem, which might be the most significant thing here. All right, thank you for watching.